why do things dissolve? So in order to look at this, we're going to use water as an example. Very good example. Oxygen, 2 hydrogens, a very polar bond here. Intermolecular force, hydrogen bonding. If I were to draw out just a little model of a beaker, very large beaker, and I were to say I wanted to dissolve something in water. We're saying this beaker is filled with water. And I wanted to dissolve, say, here on this first page, let's look at lithium nitrate, LiNO3. When I drop this in, the way that it dissolves is going to be this polar bond working its way in between our ions. So I've got lithium as a positive ion, nitrate as a negative ion. So the water is going to surround those two. We're going to get oxygen facing the lithium. We're going to get hydrogen facing the nitrate. Okay. So as these surround them, there's more energy contained in this bond than there is in the ionic bond. So this is more favorable. These bonds right here, these intermolecular forces, we call it an ionic to dipole bond. So this would be ion dipole. Because we have these dipoles in the water molecules that are splitting up these ions. If there's enough energy, they'll pull them apart. Of course, there are other factors that are involved, like we saw in our precipitation reactions when we looked at solubility. Some things don't want to get pulled apart. It's not always just a matter of having enough energy to pull them apart. So, what about something like carbon dioxide? Carbon dioxide is a gas. It's not an ionic compound. So let's look at that. Let's erase these. If I put CO2 in here, let's draw this out. We remember, between carbon and oxygen, there is a polarity. Carbon dioxide itself isn't polar because it's symmetrical, but there still are these dipoles. The oxygen is going to have a more negative sign. Now, because of that, water can still surround the carbon dioxide, just like it does with any other substance. Or any ion. And now, once this happens, these water molecules really act as a cage holding that carbon dioxide molecule inside the water. And so, even though carbon dioxide is a gas and is so much lighter, and I could bubble it through and it would somewhat escape, there would be a significant amount of it that would get trapped by these water molecules. They'll grab onto it, they'll hold it tight, keeping it in with those intermolecular forces. Now what we've got here, we've got hydrogen bonding going to straight polar bonding. So we're going to call this a dipole to dipole bond. So look at this. We've got these bonds, these intermolecular bonds holding this in place. So here we've got a dipole. dipole. Diarized. Okay. So that's how dissolving works. It all has to do with these intermolecular forces. What we're going to get into here, though, is we want to talk about the concentration of things that are dissolved. And this is commonly going to be in water. Not everything dissolves in water, and water isn't the only solvent. That's what we call something that has other stuff dissolved in it. That's the solvent. Okay, then we've got solvent. Thing that stuff, these are really technical terms, thing that stuff dissolves in, and then solute. Thing that dissolves. So there's multiple ways of describing concentration that you can see. One of them is just percent concentration. So if you buy like hydrogen peroxide at the store, or when I went out and bought some hydrochloric acid at the hardware store, it comes in this bottle, this container, that just lists the concentration in terms of a percentage. It's really inconvenient. So the stuff I bought was 31.45%. What that means is that out of 100 kilograms, or 100 grams, we'll just use grams, 31.45 grams would be the HCl, the rest would be H2O. This is really inconvenient because it means that I have to actually measure the mass of the liquid, which means I have to pour it into a container, measure the mass, figure that out, and then go back and do this math in order to figure out how much 31.45% actually is. And then I also have to do the molar mass to convert back into moles. Percentage is an extremely inconvenient way to talk about concentration. But it's something that makes sense to most people, even though they don't really, as a concept for concentration, it really doesn't make a lot of sense. People are familiar with percentages. For chemistry, though, the concentration label we want to use is called molarity. Molarity, extremely convenient, just means moles per liter. So if I have 12 molar hydrochloric acid, I would write it like this: 12 molar HCl. All that means is for every 1 liter of H2O, I have 12 moles. That is so convenient, because all I really need to do at that point is go, okay, well, how much liquid do I have? If I poured out 500 milliliters, then I'm just going to multiply this by 0.5 liters, and that'll tell me I've got 6 moles. I'll have 6 moles of HCl. That is so ridiculously easy to keep track of. So that's what we're going to do on these next 2 worksheets. You're going to just answer some questions about solutions. Just try your best. If you can't get them all, that's okay. What I really care more about is that you can do the concentrations. So if you feel stuck on the page that says solution concentration, that's just asking these general questions, screw it. Move on. What I really want you to be able to get is every single question on the page about molarity. Okay? And then we'll look at how to dilute substances, how to get this to go from 12 molar down to 6 molar, if that's what I need. Things like that, because I need different concentrations for different things. So that is next. For now, just do these 2 pages, solution concentration and molarity. Thank you.